So let's look at regularization for neural networks. I'm going to go through two parts about weight decay and weight elimination. For weight decay, we want to understand that by regularizing, we're trying to go towards simpler functions. So let's understand what a network looks like when we have small weights for a neural network. Well, in this case, as we saw from the universal approximation part, when we have small weights, we tend to be operating in this area where our linear combination is basically using a very, very gentle sloping line, right? So we saw something quite flat in the universal approximation section. But when we tune our weights to be very large, they become more like step functions, like this hard threshold, which we saw from the perceptron algorithm. And using a hard threshold, we can compute any function, as we saw in the universal approximation part again. It makes it clear that we could compute a function that's very specific to the data set that we choose. So it's quite easy to overfit when we have very large weights here. So by insisting that we do weight decay and tuning things so that the square of the weights is small, we're pushing the neural network more towards a linear solution, right? More towards a single linear regression type of output. Secondly, for weight elimination, there's another way that we can do it. We want to do something like L1 regularization, where we're going to put fewer weights so that we get a lower complexity network out. And we're going to see this later when we get to dropout in the deep learning lecture. So the idea is we want lower complexity so that we can generalize better and not, again, tune to the specifics of the data set. And how we can do this is by using something like this formula here. If we just look at the top part of this, this is our normal L2 regularizer, right? Where we're penalizing for the square of the weights. But let's take a look at this when we add the denominator here, right? When we add the denominator, what happens when we have large and small weights? Well, if we have a very large weight, then these two terms are going to cancel each other out and the 1 becomes negligible. So we're going to have a simple unit value of 1 here. In the case of very small weights, what's going to happen? Well, these two terms are going to also cancel out, but they're going to tend towards 0, and the 1 will dominate, and so you'll get something like 0 as the output. So you can see what's going to happen here is that the small weights are going to be pushed to 0, and the big weights are going to be left alone and having a single unit value for each of the very large and significant weights. You can also do the type of regularization in kind through our validation. And we could see this earlier by saying that we're going to tune our network, but try not to tune it overly so, and by using validation, decide a stopping point when the validation error starts to go up. So by doing this through a number of epochs, then we can get a change in the training cost, right? For each time we're doing an iteration, we're changing and exploring the weight space by perturbing the weights. And so we can think of this as increasing the amount of budget that we're having per iteration. So that's exactly expanding the amount of budget that we have and regularizing less. So we have to decide where to stop by using validation as a principled way to decide when continued optimization in our training error is not going to benefit us in the testing and generalization case.